What is up, friends? Welcome to our GMAT free prep hour. It is Monday, February 3rd, 2025, crazy enough. My name is Whitney, or Whit. I'm coming to you from Durham, North Carolina. It's about 6 o'clock Eastern time. For those of you familiar with the US, Durham is in North Carolina. We're right outside of the capital of North Carolina, Raleigh. For those of you maybe not as familiar with the geography of the US, Durham, North Carolina. Well, North Carolina is on the East Coast, about halfway between New York and Florida. If you were to look like over at the east side, the right side of the country, we're kind of like an elbow that's jutted out. We're a very cool state. I love it here. But for those of you in on this GMAT journey, you probably best know us because of Duke University, which is right up the road from me. So a pleasure to have you all here. This evening, we are going to be doing a quantitative free prep hour. So let me go ahead and get it up here and shared for you. So our free prep hour this evening is on everybody's favorite topic, combinatorics. Lots of people come to me for like one-on-one tutoring or for classes, and I'll ask the question like, hey, tell me about you. What are some areas that you feel like, you are strengths? What are some areas where you'd like to work? And it's like without fail, everyone says this. Some variation. Sometimes people are trying to work out the pronunciation of it. And so sometimes people will be like combinatrix, right? Or whatever. But it's combinatorics. Doesn't really matter what you call it. But this is the study of choices, about how many ways, arrangements and ordering, how many ways you can do something. And I do think for a really long time, there was this big push to sort of relegate combinatorics and probability to the like hinterland. The idea that, if you weren't comfortable with exponents and percentages and these much more pervasive topics, that you should leave something like combinatorics and probability off the table for a while. But I'm starting to feel a little bit differently, especially with the new GMAT and the way its scoring algorithm has changed. I think it is useful to have at least a base level understanding of topics that are weird, even like combinatorics. So this will be like a two-part series. Tonight we'll be doing combinatorics, and in an upcoming session, I'll do a probability lesson as well. But tonight, I'm going to kind of pull us out of full questions. We'll be doing full questions, but we won't have any answer choices. That's because I've only seen one exception in the, I don't know, few hundred probability and combinatorics questions that I've seen on the GMAT and its subsidiaries, like the executive assessment. I've only seen one question where you work backwards. And even then, you don't really work backwards. This is generally a question type where you have to get to the answer. You're not going to estimate the answer generally either. And so tonight, we're just going to focus on how to solve. So you might know, if you hung out with me, that I'm a big fan of methods that involve using the answer choices and picking our numbers. Combinatorics and probability are honestly one of these areas where we just have to kind of understand a method. Now, I'm doing combinatorics first because a lot of probability questions are layered combinatorics. Yeah, so we're going to get the tools of combinatorics down, and then in a follow-up, we'll talk about how we expand that into probability, and then we'll take probability in its own ways. So probability is more common on the test than combinatorics by at least in terms of what practice questions have been released, there are 3 to 4 times as many probability questions as there are combinatorics. But a lot of probability questions require some combinatorics work underneath. Yeah, and hopefully I have my old pup over here, Lexi. She's like 13 and a half, so she's milling about in the background. She also doesn't like combinatorics. She's not a fan. All right, so we're going to get started. What we'll cover this evening are concepts like, how do we even determine arrangement or choosing? Like, what does that mean? And then we'll look at 2 different methods for visualizing. I would say that they're both very good methods. In some scenarios, one method is a little bit more powerful than the other, but they're actually the same method. It's just 2 ways of visualizing the same thing. So I'd like for you to feel comfortable with both, actually. So we're going to look at 2 of these methods, and then we'll talk about variations on how these, choose and order stories happen. in this world of combinatorics, you may have heard things like permutations and combinations, and I'm going to invite you to chuck that. Because actually, if you really want to kind of like Google a little about combinatorics, there's like an umbrella concept in combinatorics. It is this idea of partitions. So, excuse me, what we're going to be thinking about when we think about like choosing and combining is partitioning, sorting people or things into groups. Now, for those of you, again, already familiar, the concepts of permutation or combination have something to do with like whether people's order is allowed to shuffle. And that's actually the thing that I think gets people the most confused is this like, oh gosh, should I call it a permutation? Should I call it a, but we're just gonna throw it out. Our goal is to just like understand what it means to take a big group of people and separate them. And that separation might have them have a specific order or maybe just specific groupings. Yeah. So if you have this like combinations and permutations sort of in your head, I'm going to invite you for the next 50-ish minutes to maybe like set it aside because for a lot of the questions that you'll see on the test, trying to make that decision overcomplicates things. Yeah. So stick with me. I promise I'll try and make this a little bit more straightforward than maybe it has felt to you before. So we're going to start with a really kind of what we would consider in the world of combinatorics, a very intro, basic combinations problem. Okay, so give it a read. And I want you to feel free to type in the chat window. What do you think the answer is? And more importantly, how did you solve it? Right? Like, what did you end up doing? So we'll take about a minute. Again, for a lot of these, it's you either know how to do it or you don't. So we're not going to spend, 2, 3 minutes. But take about a minute to think about this. All right. I have a couple of guesses coming in to the like hosts and panelists. So this is an example of what we're going to call the like fundamental counting principle. This idea that if I have an ordered set of choices that I have to make, and I want to think about how many total paths I can take through this like maze of choices, there's two things that we want to think of, two words we want to think of. We want to think of the word and we want to think of the word or. Okay, so the word and is this concept that two things have to happen at the same time or together in order to get the outcome we want. So in this story, as a diner at the restaurant, I have to order an appetizer, I have to order a main, and I have to order a dessert in order to achieve 3-course meal. Yeah, so I have to get app, main, dessert. Now, within those choices, though, I have an or choice. I have 3 different appetizers. I could choose, you know, bread and butter, I could choose salad, or I could choose soup, right? Those are my like 3 appetizers. And this idea of or, meaning that I'm going to select one or another. Okay. So when we think of these 2 words, just as like a little quick aside, we'll kind of add in over here. When I think of the word and, an and sort of choice, does anybody know what that implies in math? An and choice? Mm, close, not quite. That's actually our or choice. If 2 things both have to happen, and you can think about this sometimes more like in a probability, because sometimes we're more comfortable with probability. Like if I have 2 things that have to happen at the same time, yeah, this is going to be multiplication. And if I have an or choice, that means addition. So for example, let's look just at the appetizer. I can choose bread, salad, or soup. One or one of these 3, right? How many choices do I have just in the appetizers? If I can choose bread, salad, or soup. Exactly, 3. I add them together. Yeah. Now, one of the things we can kind of look at, let's imagine under our appetizers, we have like, A1, A2, and then A3. And then in our mains, we have 4 of those: main 1, main 2, main 3, and main 4. Let's ignore desserts for a second. For every appetizer, right? So let's say I pick appetizer 1 and pick the bread. For each appetizer, I have 4 possible mains that could then follow. The chicken, the fish, the veggie, the steak, or something like that, right? The beef. That's true for all 3 of my appetizers. So I have these 4 mains that would go with this appetizer. Same 4 mains could go with the second appetizer. Same 4 mains could go with the third appetizer, which means if I have 3 choices for the first, followed by 4 choices for the second, that should add up to 12 total choices because I have to pick an appetizer and a main. Right? So this is where our multiplicative comes in, and is multiplication. Because I have to choose an appetizer and I have to choose a main, I'm going to multiply my 3 times 4 and get 12 total possible combinations of appetizers and mains. So we can start to see that as the number of things we're choosing from within grows, this is going to balloon. And then if we've got 2 desserts, yummy, yummy desserts, 2 desserts, I'll do these in red. That makes them more fun, I think. So if I've got 2 desserts, dessert 1 and dessert 2, right? For any main I choose, I've got 2 desserts. So for one appetizer, I have 4 mains. For each of those mains, that's 2 desserts. So that's 2 and 2 and 2 and 2. And then I have to, of each of those appetizers, which means the total, wow, I could not get a color to work. My apologies, guys. The total number of combinations, right? So the total number of ways that I can, as a diner, choose is 3 times 4 times 2. So 12 times 2 or 24. Yeah. That is literally combination. Now, you should be sitting there being like, Whitney, they're not all simple. You're exactly right. They're not. But this is the sort of fundamental counting principle, right? The thing that we want to kind of see here is that if we were given this question, just as it is, and not like drawing the whole thing out. Okay, so for our 3-course meal, what I could do is go, okay, and we're going to start with the slot method because I think that the slot method is generally super flexible so long as we understand how to apply, right? So I think the slot method, in my opinion, can be applied more broadly. There's at least one case where the other method we're going to look at, the anagram method, is a little bit easier to visualize. But slot method would say this. I have 3 choices. I have an appetizer choice, and I usually label my choices. I have an appetizer choice. I have a main choice, and I have a dessert choice. And the crucial thing about naming these slots is thinking to myself, do they actually have different names? Like in this case, they do. Like the first slot is an appetizer. That is different than a main. That is different than a dessert. And in this case, I have 3 choices for my appetizers, 4 choices for my main, 2 choices for my dessert, because it is mandatorily a 3-course meal. That means, and I have to pick all 3. I'm going to multiply across and get to 12. I'm at 24. Good Lord. Ignore me for a second. Head colds result in bad math, clearly. Okay, scale of 1 to 5. 1 being least comfortable, 5 being most. How do we feel? Phenom. Try it again. Let's like level this up a little bit more complicated. Again, I'll just almost set a timer going up. Let's shoot for like a minute and a half, somewhere in there on this one. All right, if you haven't, hit me with a guess. Let's see what y'all think about this one. I've got a few different answers, which I love. Okay, if we're going to do this with a slot method, how many slots are we building? Yeah, we're going to do 5. And we're going to label them. I don't really know the order of the test, but whatever. We'll call this like Q1, Q2, Q3, Q4, Q5. It's not a G, that's a Q. And then how many choices does Caroline have for the first question? I'm going to choose these and however we want. Sure. Let's go ahead with the multiple choice one. She's got 4 choices for the first, and there are 3 multiple choice questions, so it's 4 and 4. And then what about the last 2? What's true about the other 2? She has 2 choices each. Yeah, exactly. All right, and then what do we do? Does she have to answer all 5 questions? What does it say? Yeah, it says that Caroline selects 1 answer for every question. So then what is her probability? Well, I would multiply all these out. Now, let's not forget, a really annoying factoid about the GMAT is that we don't get a calculator. So it could be really useful to learn. I like to kind of pass along the things I want to make sure you memorize whenever they come up. So you definitely want your multiplication tables, right? You want to be able to multiply everything up through 10. I also like the 11, 12, 13s like times each other. So like 11 times 12 and 13, 12 and like 12 times 13, 12 times itself, that sort of thing, 13 times itself. I also like the small powers of numbers like 2, 3, 4, and 5. So like 2 to the power of from 1 all the way up to 2 to the power of 10. 3 from the power of first to the fourth. 4 from the first power to the fifth power, and 5 up from like power of 1 to power of 3. So like what's 5 cubed? So does anybody know what power of 2 this is? Let's see if we can practice your exponent rules. How many 2's are being multiplied right now? Because each of these 4s, each 4 is technically 2 2's, right? So you could see this number as 2 different values that I would want you to have memorized. This is either 1, 2, 3, 4's, and that's another one. So this would be 4 to the 4th. Or this is also 2 to the 8th. Again, give yourself some flashcards here. They may know what 2 to the 8th is. Not quite. 256. Exactly. So how many different ways, with just a 5-question test, could Caroline select an answer for every question? 256 different ways. That's a lot, right? Because she has to answer them all. Of course. Yeah, Jess, anytime. Please ask away. Any questions, by all means, y'all ask away. Or is addition. So notice that these questions are, so all of these, if we think about these questions, such a good question. Thank you for that, by the way, Jess. These 3 questions, if we were to look at them, right, they'd probably be like A, B, C, D, E, or A, B, C, D, excuse me. So how can she answer these questions? These questions could be answered by saying A, or B, or C, or D. There's 4 choices. She can choose from any one of them, and so they get added together. Same with true or false. Within the question, it's an or, it's an either or. But because she has to answer that question, the string across is always multiplication. Let me give you such a good question. Let me give you an example of how or, because it doesn't show up all that frequently. But let me give you, I'll give you an example of how or shows up in combinatorics. Of course, yeah, totally. Quick question. Any other questions about the one as is? Cool. So from a 1 to 5, for right now, how do we feel about like, okay, if I have this many choices, how many? Does this feel, how we feel? 1 to 5. We're gonna do an example. Great, I love it. Okay, so now let's imagine a story where you can, let's, I'll have to kind of write this one because they don't really exist all that often. But Caroline gets to choose either dinner and a movie, or let's go dinner and a movie, or ice cream and a concert for a date night. For she has 3 dinner options and 4 movie options. Or I'll say it. Okay. There are 3 dinner options, 4 movie options, 4 ice cream options, and 2 concert options. How many different possible date nights can Caroline choose from? So let's take a second and think about it. I know it's like a very strange question, but still. And if you think you have a guess, feel free to put it in the chat. Okay. Let's think about Caroline's choices. What's one kind of like choice that she could make? So what's one of her kind of options? So I always try to put myself in the story for combinatorics type stuff. Okay, so she could choose to do dinner and a movie. And then once she does that, right? So if we think about it this way, she could go the dinner and a movie route. It's like it's an ampersand. Right? Like this is and a movie. Or she could go ice cream, and a concert. Once she's decided I want to go dinner and a movie, how many options are there inside the dinner and a movie scenario? Yeah, inside dinner and a movie scenario, she's got 3 dinner options and 4 movie options. And in order for her to have dinner and a movie, she has to do both. So 12 dinner and a movie options. Alternatively, if she had chosen ice cream and concert, how many possible choices would she have? Well, she'd have ice cream, concert, 4 ice cream options, 2 concert options, so 8. Which means if I were to, let's say I knew what all those dinner, movie, ice cream, and concerts, if I'd listed them all out under dinner and a movie, I'd have 12 date possibilities. Under ice cream and a concert, I'd have 8. She's choosing from these or from these, bringing together a total of 12 plus 8 or 20 total possible selection. This is where or comes in. Does that, Jet? Perfect. So what we're thinking about when we're building our slots or we have numbers, like we're like, okay, I have this many choices. Right? I have 3 choices and I have 4 choices. 3 choices, sub choices, 4 sub choices. We rarely think about the and inside of those because usually what's in them is an or. You can pick this dinner place or that dinner place or that dinner place. So we don't usually think about that one. So I wish. I wish. Wouldn't that be more fun? I really wish you could tag team this stuff. Like I absolutely wish that you could have like a person and the two of you together. And like you reach out and you select somebody that's like got your perfectly matched, right? Like your strengths are their weaknesses and vice versa. It'd be so much more fun. Be way less stressful too. All right, but so we've got this idea of, all right, this is what and, this is or. Heads up, or not as common, much more rare. All right, so now how do we feel? Scale of like 1 to 5. All right, if I'm making like a string of choices, I'm starting to see what and versus or means. How we feeling? Okay, amazing. Okay, so we're gonna step up things a bit here. Okay, we're gonna look at what these are gonna be more like. I mean, and these are fully likely questions, by the way. What we just saw, totally legitimate questions. Totally legitimate questions. Okay, the next level of combinatorics is often in this idea of like codes. And so, just as a little bit of foreshadowing, in the world of codes, just like in the world that we saw before, right? In this world with dinner and movie, notice that every slot had its own name. Question 1, question 2, question 3, question 4, right? Every slot was like, okay, it's a dinner slot, movie slot. They're not interchangeable. This is also true of codes, right? Because if we think about a typical code, something being the first number is different than if it was like the third number, right? Like I could use the numbers 1, 2, 3, 4, 5, and every rearrangement, every what some people will call permutation of that, every version of 1 through 5 is a different code, meaning that each slot we build, because a little bit of a tip, we're going to use slots again for this one. Each slot we build is a spot that matters. It's like okay, this is going to be the first number in our code, and this is going to be the second number in our code, and the third number in our code, and so on. Okay. So I want you to think to yourself, how might you answer this one? Kind of based on what we did before, thinking about like, well, how many choices do I have? How many options do I have? Okay, I got lots of guesses coming in. So we've got 4 spots. Okay, and I want to think to myself, all right, these 4 spots, like here's spot 1, spot 2, spot 3, spot 4. How many choices do I have for my first digit? Well, this isn't a 4-digit number. So one side note, if they had said a 4-digit number, not a lot code, but a number, would there be a restriction on my choice for the first number? So if I want to think of a 4-digit number, let's think about what all the digits are, 0 through 9. Yeah, the first digit couldn't be 0. if this were a number. Okay, so just a little bit of care here, because the number 0134 is actually just 134. But because this is a code, we can put whatever number wherever we want. And so, how many possible options do I have for the first digit of my lock code in this situation? I have 10. I have 10 options. I can pick any of the numbers from 0 to 9. I'm gonna pick, I have 10. How about the second one? So some people are telling me I only have 9. But what does that imply? Why don't I have 10? Nowhere does it tell me that my numbers can't repeat. So it would need to tell me that. It would need to say 4-digit lock code from the digits without repeating. So for this one, I go, oh, okay, I can choose 10 for my second one. I could choose 10 for my third, and I could choose 10 for my fourth. This is, in order to get a 4-digit code, I have to do all of them. And so this is 10 to the fourth, or a 1 with 1, 2, 3, 4 zeros. Notice it's the exact same thing. We're going to think, how many choices do I have? How many choices do I have for the people that go in this spot? I have 10. Let's look at what happens when we do start to get edits. Okay, so let's imagine, same generic story. However, I have some limitations. So how many options do I have for my first spot? Because it says the first and the last digit have to be odds. That'd be 1, 3, 5, 7, 9. Okay, so that would have to be one of 5. Are there any limits on my second digit? No. So that one could be 10. Are there any limits on my third digit? No. How about my fourth digit? It has to be 5. And so 5 times 5, 25 with 2 zeros. Now, I didn't write them here, but I do think it's really important to be like, this is digit 1, digit 2, digit 3, digit 4. Digit 1, digit 2, digit 3, digit 4. I think that's really essential. Hasn't mattered yet, but it's going to. Let's go one more. So all of the previous rules are thrown out. We're like, new scenario. Okay, How many choices for our first? Yep. But this time, how many choices for our second? Beautiful. So when we start to see without repetition, there's this like dropping off. So I picked 10 for my first, but now I only have 9 left because I've already picked a number. And now I've picked 2 numbers, so I've only got 8 and then 7. So I have to multiply these together. I did 9 times 7 is 63 times 80. So 80 times 63. So 6 times 8 is 48 with 2 zeros. 8 times 3 is 24 with 1 0. And so this is 4,800 plus 200 is 5,040. If you're looking at this and thinking like, what did you just do and how did you just do that math? Come hang out with me next weekend. Because this coming weekend, I'll be doing the Foundations of Math workshop where we do both how to do this kind of computation, but even like a million other types of computation pretty quickly. Yeah, so that's coming up this weekend. All right. Well, let's try another. But before we do, again, let me check in. How are we feeling? With like, all right, I got to come up with some codes and maybe there's some restrictions. 1 being least comfortable, 5 being the most. Okay. And if there's anything that is sticky, that you're like, I don't like it, I don't get it, I'm a little stuck, I'm confused, talk to me. Tell me what it is. I want to hear about it. So far, most everybody's like fair to Midland about it. So yeah, no, that's what I mean. I think that's actually good. Like I think that's a good one. I think 3.5 is good. It's like I'm just like a little better than halfway, which is fine. Like this is still new. But if there is anything that you're sitting there like, okay, here's where I'm stuck. Please ask the question because you aren't alone. Um, D as a digit. What do you mean D is a digit? Oh, a 0. Sorry, my contact was yes. No, it is not an odd. So great question. Is 0 odd, even, both, or neither? It's my favorite. I love 0. It's so bananas. 0 is, drum roll, even. 0 is even. Fun enough. Next, is 0 positive, negative, both, or neither? If you come to the workshop this coming weekend, I'll quiz you on it again. Fear not. It is neither. Yeah, exactly right. So 0 is even. It is neither positive nor negative. So that's where the 5s come from because my odds are just 1, 3, 5, 7 in mine. Yeah. Great question. Thank you for asking it. Oh, yeah. The multiplication, like I will tell you this, the more and more I encounter the newer GMAT questions for like the new focus stuff, the more I understand how important it is to be able to do multiplication and division of ugly numbers quickly. So I'm dead serious. If you haven't, come attend our free Foundations of Math workshop this weekend. We're going to be doing lots of this stuff. Not combinatorics, but lots of getting at computation quickly. No, it is definitely not easier than the one before. Question in the chat window is the new GMAT easier? No. I would argue that in some ways it's more tricky than the previous. It dropped some topics, like geometry, but it beefed up the difficulty in the areas it didn't drop, in my opinion. I know. Sad face for me too. All right, let's try another. Let's keep tweaking. And we're going to think a little bit about why this one's different. How is this one different? Because it's going to, it feels like the story alone feels different. At least to me, it feels different. Yeah, I had one thought, like, why is this weird? Because like not everybody is participating. Also, I want to draw your attention to the previous stories. In the first story, you had very clear choices like, okay, you're going to make a choice for this meal and this meal and this meal, or like this date or this movie or this whatever. Or it was very clear that like this was spot one, like spot one in a code, and here's spot two in a code, here's spot three in a code, and here's spot four. This is where we start to get into this, like the other variant of how combinatoric stories are told, which is like choice. I'm going to have a group and then I'm going to choose some people from that group. Now, again, you might have this like recollection of like, well, am I going to choose them and order them? Am I going to choose them and just group them? Like, okay. So again, we're going to like set that off to the side. What I want you to think about is that this is still fundamentally a slot method solvable problem of choice. However, there's something different. What's different about like having a combination lock and like choosing a group of 4 people? They might have a sense of what might be different about like the slots related to a combination lock and the slots related to the 4 people I've just chosen to be on a committee. Yeah, I definitely cannot repeat people. Dead given. Yeah. That's a big one, which could also be true on the combos, right? We saw a combination lock where they could call repeats out. But like, let me ask this, or let me sort of maybe like, I'm gonna borrow y'all. So let's say that for this group, so I can get some different names. For this group, we're gonna select. I'm gonna go with one specific selection. Okay. So let's say for this group, we select Ginny. We're gonna pick you for the first spot, and then Jess, we're gonna pick you for the second spot, and then Melissa, we're gonna pick you for the third spot, and then Ronnie, we're gonna pick you for the fourth spot. Okay. So the 4 of you have been selected. Is that different than if I'd picked Ronnie first, Jess still second, Jenny third, and then Melissa fourth? Are those like 2 different selections of 4? No, the 4 of you have still been chosen. And it wouldn't matter if I decided to pick Jess first, and then Melissa, right? And then Ronnie, and then Jenny. This is this idea of like, kind of like, these slots aren't distinguishable. These slots are like, I chose you, right? Like I chose you. So before we jump in and try to come up with a number of options, right, I want to show you 2 ways that we're going to do this. Let me show you how this is going to look with the slot method first. Okay. The way this works with the slot method, and let's go with like a little simple example so I can prove it to you. We're going to do the same group, but this time we're just going to pick, let's go with a much smaller number. Let's say we've got 5 students, and we're going to pick 3 of them. Okay. So my students are going to be, A, B, C, D, and E. And now let's say I'm going to pick my first 3 people. So I'm going to pick A, B, and C. Choosing A, B, and C, how many ways could I order these 3 people? How many different ways can you order 3 people? Well, if I wanted to write them out, I could keep A first and then switch C and B. I could go with B first, followed by AC, keep B first, but switch the other 2. So we're going to be really methodical. Or I could put C first, go A, B, keep C first, and switch the other 2. Did I miss any? What do you think? Did I miss any? No, I didn't miss any. So for example, let's imagine, I'm going to change this even more simply. Let's say 3 students have volunteered. Right? 3 students have volunteered, and 3 students are going to be chosen. If 3 students volunteer, and from those 3 people, 3 were chosen, how many different groups of 3 could I have? This is gonna sound like the dumbest question, I know. But if I have 3 people, and I'm gonna choose 3 people from those 3 people, the answer had better give me 1. However, if I go with a traditional slot method without adjustment, I have 3 people I can choose for the first. I have 2 people I can choose for the second. I have 1 person I can choose for the third. We'll hold the phone. This is how many ways I can order 3 people. So in order for me to have this not include an order, because I want to be able to shuffle them, and it doesn't matter, because these are all the same in this universe. You're going to take the number of spaces that are all interchangeable, and you're going to divide by that number factorial. Because it turns out that the number of ways to order n things is n factorial, where 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. Sorry, my handwriting is really scratchy. 5 factorial, 5 times 4 times 3, just like that. Okay. So a factorial is nothing exciting. They can get pretty big, but it's just whatever that number is times each integer smaller until you get to 1. So we haven't had to do this yet, because in every previous example, they were interchangeable. They were not interchangeable. Slot 1, slot 2, slot 3, and slot 4 were clearly different things. It was the first digit, the second digit, the third digit, the fourth digit. It was the first question, the second question, the third question, the fourth question. They were distinct, right? In this case, it was the appetizer, it was the main, it was the dessert. But all of a sudden, right, when I come here to my 8 students have volunteered, I got 1, 2, 3, 4. I've got to think I have 8 students for my first that I've chosen. Then I can choose 7. Then I can choose 6. And then I can choose 5. However, these are all, present, 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 present. They're all the exact same. So because these are all the same, they're all just like presenter, not like presenter number 1. It doesn't tell me in order. It just says present. Because of that, I have to take this product and I have to divide it by 4 factorial. So this will be 8 times 7 times 6 times 5 divided by 4 times 3 times 2 times 1. And we'll cancel stuff like 4 and 2 cancel out my 8. 3 cancels out part of my 6. 2 and 5 is 10 times 7 is 70. What about the second story? I promise we're going to do more examples of them. But what about the second story? I should say present for an hour on every hour. What goes under each slot this time? Something seems a little different though, right? There's like another rule. The first one just said how many groups. The second one says how many schedules. So this one was like a person, presenter, 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 presenter. The fact that I called you a presenter here and I called you a presenter here were no different. But how do I label my slots here? What does the story tell me? Yeah, this one is our times. So I've got somebody going in at the 1 p.m. I've got somebody going in at the 2 p.m. I've got somebody going in at the 3 p.m. I've got somebody going in at the 4 p.m. The numbers on top are going to be the same. However, each one of these is distinct. Every single one of these is different. So if I had, A, B, C, D, that's a different schedule than if I had D, A, B, C. Those are two different schedules. In one of them, A went first, and another one, D went first. Mm-hmm. So what I want to show you, one of the things that can be helpful here is this idea of, so let me come back to this. Let's go back to the original one, and then we'll look at a few variations on it. It can be a little helpful to think about selection. So again, I had mentioned this word, and I'll say it again. It's this word called partitioning. So when you're taking a group and you're selecting from them, sometimes it can be helpful to think of this as a partitioning, a grouping. So the slot method, just so you can see what it looks like, I want you to see that they're the same. The math is going to be the same. The slot method, as you would solve this, would be to say, okay, all of these, this is the first question, not the second one. This is the first one. I'll show you how we'll apply this to the second one. And another like hybrid. Since these are all the same, like 4 are the same. Up top, we've got our, I have 8 kids I can choose from for my first pick, 7 for my second, 6 for my third, 5 for my fourth. This is going to be 8 times 7 times 6 times 5 divided by 4 factorial. Okay, I'm going to give you a different visualization that can be helpful. I think, at least, it can be helpful. And this is the idea of the anagram. Okay, so the way the anagram works is that we will create spaces. So I'm going to build like a little baby table. I'll show you what this will look like. One second. All right, so if I create myself a little table, that has spaces to label everybody. Okay. So let's say this. Okay. So I'm going to have my like 8 kids. So here's kid 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so I've kind of created a like a worksheet where I'm gonna figure out what to do with everybody. In this first story, what am I gonna do with everybody? So how many people are gonna get chosen in this first story? 4 of them. Yep, exactly. So what I'll do is if, like I'm the coach or the science professor or whatever, I'm going to look at my little table that has everybody's name on it, names 1 through 8. And I'm going to put over like underneath each person. All right, I'm going to choose you. So I'm going to choose these 4. Right? They've all been chosen to present, or maybe I'll keep the letters the same so it's easier to see. So you're going to be a presenter, you're going to be a presenter, you're going to be a presenter, and you're going to be a presenter. What do I do with the other 4 people? Because they have to be labeled as well. So what am I going to do with that? Everybody gets a partition. Yeah, and be like, you're out. And what this does, so the world of partition, it's actually a formula. So the formula for a partitioning, meaning I'm going to take a big group and I'm going to separate it. The partition formula is as follows. It's, the total that I'm choosing from goes on the top. That with a factorial symbol. Right? The math just, remember how we did the fundamental counting principle and it was like, hey, this is how you get there. You just multiply those 3 things together. Or how many ways can you order n things? You order it n factorial. The math is that you take the top total that you're choosing from, and then on the bottom, it's partition 1 factorial, partition 2 times partition 2 factorial times partition 3 factorial, and on and on and on and on and on until you've put every single person in a partition where all of these partitions plus partition 3, plus blah, 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 equals the total. They all have to add up. So when I'm doing a selection, so now let's look at a few variants of this. So I'm gonna show you what a bunch of these look like with just a partition and not the slot, and then you'll see how how we can use a slot now that we know how the math works. My first story of my 8 science fair kiddos, right, where I'm going to just choose 4. I'm going to choose 1, 2, 3, 4 to present, and 4 of them are left out. The math for this then results in 8 factorial divided by 4 factorial, 4 factorial. And actually, if I keep it over here, sorry, let me put it back over here for a second. This becomes 8 factorial divided by 4 factorial, 4 factorial. What is 8 factorial divided by 4 factorial? Not what number, don't multiply it out, but what is left when I divide 8 factorial by 4 factorial? You might write it down on your paper, 8765432 over 4 factorial. Yep, it is this part. Be careful, we don't divide that way. You have to write this number out. So 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 factorial times, I'll do the other one, 4 times 3 times 2 times 1. These 4s, these 3s, these 2s, these 1s are all going to cancel. And notice what's left. 8 times 7 times 6 times 5 divided by 4 factorial. Exactly what we have here. So let's look at the kind of anagram. So this is what we call the anagram method. Let's look at this with a different example. So what if I applied this to my example of my 8 kids who are going to present everywhere from 1 p.m. until 5 p.m. How do we fill in the blanks? So how do I assign my first one? So last time we said, you present, you present, you present, you present, you. This time I'm not just going to tell you that you present. I'm going to tell you present and what else? And when. Yep. So I'm going to call you 1 p.m. All right. So I'll make you this is my 1 p.m.er. This is my 2 p.m. This is my 3 p.m. This will be my 4 p.m. And then what happens to the other 4 people? I'm actually going to need to make a little more space. Yeah, they get an X again. Everyone gets partitioned. Everyone gets partitioned. So everybody's got to have an assignment. Now, this is where it gets a little, again, I have to represent the numerator as everybody. How many partitions are across the bottom? In this example, I had 2 partitions. I had one here, and I had one here. This one had 4 people in it, and this one had 4 people in it. How many partitions do I have now? Yeah, I have this one, this one, this one, and this one, and this one. How many people are in each of my first partitions? Yeah, and so these are technically 1 factorial, 1 factorial, 1 factorial, 1 factorial, which is just 1, and then 4 factorial. So this would be 8 factorial divided by a bunch of 1s, 1, 2, 3, 4 1s, a bunch of these little 1 factorials, and then 4 factorial. You would write out your 8, you'd write out your 4, and you cancel everything and simplify. Okay, before we do that, let's look at the third example. So for those of you who are familiar with combinatorics and probability, or combinatorics, the first one is the most simplistic case where we separate people in and out. This is what's technically called a combination. The second one is that we perfectly choose and perfectly order. That would be technically called a permutation. However, they're both just variants on partition. So if we understand that everyone has to be partitioned, then we can escape pure combination, pure permutation, and we can figure out a problem like this last one. They are not. I made them up. Good question, though. So I've got 8 students. I can equally choose from all 8 of them. So there's not limitations. So what am I going to label my first person? Because this isn't me just picking 4 people anymore. I'm still choosing 4 people, but I'm choosing them and doing what? I'm choosing them and doing what? I'm choosing and then sub-assigning. Exactly, I'm partitioning. I'm like, okay, I'm choosing you, but I'm also giving you a specific assignment. You're not just being chosen. You're being chosen and told that you're doing geography. You're being chosen and told that you're doing chemistry. So I've got 1 kid doing geo. I've got 1 kid doing chemistry. I've got 2 kids doing bio. And then I got 4 kids that aren't going to be engaged. So I want you to think for a second. If this is how it's labeled, what's the fraction going to be? My numerator is still going to be that 8. It's going to be whatever this number is across the top. My denominator, how many partitions do I have? Yep, I got 4. So I got like 1 person here, 1 person here. I got 2 people in that one. I got 4 people in this one. And exactly, my math is going to be 1 factorial, 1 factorial, 2 factorial, 4 factorial. And I'll usually go back and just double check and make sure they add up. 4, 5, 6, 7, 8. Yep, I covered everybody. I mean, you've covered everybody if you've made your little table. And so what we get is, 8 factorial with a 4 factorial thrown out is the same as 8 times 7 times 6 times 5. So if I was going to take this exact same set of questions and I was going to do them, so here I'll leave the, I'm going to take the little images out. Oops, hold on, didn't want to erase all of that, just this part. So I can show you that if you like the slot method is still universally applicable. You can still use it here. You can use either. Notice I have 8 students. I'm choosing 4. 1, 2, 3, 4. They're all being chosen to present, 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 present. And so up top, I've got 8, 7, 6, and 5. This would be 8 times 7 times 6 times 5 divided by 4 factorial, which is exactly what we get when we divide this 8 by that 4. We get this 8 times 7 times 6 times 5. If I did the slot method for the second one, it's still 4 people getting chosen. Still my 8, 7, 6, and 5. But this time, I got 1 p.m., 2 p.m., 3 p.m., 4 p.m. So since they're all different, I end up not dividing by 8. I just multiply them together because these are all of these little ones. This is this 4. Or in our last one, I got 4 slots. 1, 2, 3, 4. I got a geography slot. I've got chemistry and 2 bios. And so these 2 need to divide a 2 factorial out because they're lumped together. And I've got my 8, 7, 6, and 5. Notice that my 1 factorials just fall out because they just equal 1, so we don't end up writing them. And then the remaining, like who was not chosen, got divided out because I didn't create slots. You can use either method you want. So what you might do is say, if something provides like a much more clear, okay, I've got a meal and a appetizer or dessert, I'm choosing from these 3 different categories, and then I've got to choose them all. Or if it's like some digit or passcode, I'm going to go slot method. If it's selection from a bigger group, I'm going to go, partitioning, these kind of partitions, then heck yeah. Right? Like totally okay. The answer would be different if it was 8 times 7 divided by 2 factorial. Yeah, for sure. If that 6 and the 5 weren't there, that'd be me only selecting 2 people. So that would be 8 people. I chose 2, and their order doesn't matter. Why does which last one have a 4 factorial at the bottom? They all have a 4 factorial at the bottom from the previous version that we did of them. Right, the 4 factorial on these came from the anagram version. Yep, exactly. Oh yeah, it's a great question. Anybody can answer? I got a great question in the chat window. Why did I put the 2 factorial under the 6 and the 5 and not the 8 and the 7? It's technically going to be under all of them, by the way. When I go to write these down, this is going to be 8, 7, 6, 5 divided by 4 times 3 times 2 times 1. This is just going to be 8 times 7 times 6 times 5. This one's going to be 8 times 7 times 6 times 5. If I wanted to be thorough, I would divide this by 1 factorial. 1, right, this would be 1, 1, 2. But why did I put a 2 factorial under the 6 and the 5 in this one? And this equation over here, you wouldn't get from the slots. This is from the other method. I just wanted you to see that they're the same. Nope. It depends, right? This is what I mean. It depends on which method, right? If you use the slot method, you're going to be doing all this stuff in the green. If you use the anagram method, you're going to be spitting out this in blue. But what I wanted you to see is that the math is the same. You're going to end up in the same place, whether you use the anagram or whether you use the slots. It'll take you to the exact same place. Yep, exact same place. And the reason why I put a 2 under the 6 and 5 is a note to myself because, hey, these 2 things are actually the same. So every time I've got, this is where the slot method can be a little bit more confusing because I have to remember, are those slots labeled the same way? Oh, they're both bio. So I have to see that as a partition of 2 that I have to divide by. Yeah. All right, let's try one. How would you handle this? We're gonna add just like a little bit of complexity before we call it a night. I know we're over for sure, but I want to give you the last like couple of versions you might see. But I did want to try one more of these. All right, let's start with anagram. What goes up top is the number of people I choose from. I'm choosing from 10. And then what am I going to label my first block? For anybody that used this method, what am I going to label as my first block? Yeah, I'm going to label a P for sure. Beautiful. I'll label it a P. And then what am I going to label my second block? VP. What about my third block? Yeah, nice, y'all. Secretary. And then what do I label 4 through 10? Bunch of X's. Right, I'm just gonna be lazy. Bunch of X's. So I'm gonna write this as a factorial. So what is this gonna look like as my factorial? When I write out the fraction. That's gonna be the bottom. What's the top gonna be? Yes, exactly. Beautiful, y'all. Beautiful. So it's gonna be 10 factorial divided by a bunch of ones and then a 7. If I wanted to do this with slots, boop, 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 I've got a president slot, a vice president slot, and a secretary. Because they're all three different, I don't have to divide anything. And my numerators will be 10 people for my first choice, 9, and then 8. I multiply those three numbers together. Again, we often do a little less math if we're doing this, or we write a little less if we're doing the slot method. We just need to make sure that we remember, okay, P, VP, and S, those three things are different. So it would be like dividing by 1, 1, and 1. Like 1 factorial, 1 factorial, 1 factorial. Okay? What about this version? Yeah. So we get to this one, still 10 students, right? But this time I've got president, vice president, 2 secretaries, and then a bunch of no's. These are all X's, drawing them poorly. And so this becomes 10 factorial over, still have a couple of 1s, but then I have a 2, and then I have a 7 down here. If we did this with the slots, boop, 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 I'm picking 4 people this time. I got 10, 9, 8, and 7. However, I need to label my slots. I got a president, I got a VP, but these 2 are both secretaries. So I usually do like a little bar to sort of show, okay, these 2 are together, so they're, right? Oh, sorry, this should be a 6. You're right, that's a 6. I can't count. This is a 6 factorial. Thank you. See, I told you I normally sit there and count them back up and down. The one time I don't do it, yeah, because 7, 8, 9, 10, 11, that would have been too many. So you're exactly right. This is a 6. Over here, I need these 2 to combine because these are the same group. I have to divide by that many things factorial. So like what you're supposed to divide out is easier if you've drawn it out with the factorial, like with this anagram method. But if you really are more comfortable with the sort of slots and can see how to make that adaptation, totally okay too. But notice they're going to get me the same place because 10 factorial with the 6, 5, 4, 3, 2, 1 canceled out is 10 times 9 times 8 times 7. They are the same. So where did this method get its name? It got its name from an actual anagram. If they ever ask you for rearranging letters, yeah, I think it still does. Hold on, let me come back. Somebody just asked about this. Why the 2 is under 8, 7. Do you get a different answer? Oh, no. Okay, I'm sorry. I see what you were asking before. Like when I did this 2 under the 6 and the 5 versus under the 8 and the 7, that wouldn't change anything. If I had done, BB and then GC, it would still be the same. I thought you meant if 8 and 7 were also the same thing, and so also had to have a 2. Totally misunderstood your question, so that was on me. Yeah, I give a bracket here to visually say these are the same. This is a group, this is a partition. So in my mind, I do the slot method and partition them. If that helps, maybe that makes a little more sense. Cool. So that's just my visual way of being like, don't forget these 2 are a partition. You better divide by 2 factorial, or like, don't forget these 3 things or these 4 things, right? Like this is my bracket. These like 4 things, they're one partition. So you better divide by 4 factorial. I don't want to forget that. Yeah. So the one that you like kind of have to do with the anagram method is the literal anagram, where an anagram is where like you can shuffle the letters of a word around. The way to do this, because you're selecting everybody, it's like really kind of a pain to do as a slot method. I mean, technically you can do it as a slot method. It's just, I don't feel like it's as intuitive. So I need 6 spaces, right? I want to figure out how many ways can I rearrange this. I need 6 spaces. So I draw 5 lines. 1, 2, 3, 4, 5. Then what I'm going to do is I'm going to rewrite these letters. So I've got a P, an E, a B. Oh, there's a second B. There's an L, and then there's an E. Because I want to put my repeats together. And so I've got my 1, 2, 3, 4, 5, 6 letters. And then I'm literally going to put them down here. P, E, E, B, B, and L. So what's my formula? Because once you've drawn it like this, it's always going to be the same. You're always going to pull from this anagram in the exact same way. Yeah, exactly. I'm going to have a 6 factorial up top. And then I've got a P, I got 2 E's, I got 2 B's, and I got 1 L every time. That's why I put my 2 E's together. See how I put my 2 E's together? So I made sure and rearranged. Like they could ask you to do this with Mississippi, because man, that's a word that's got a lot of repeats. Right. So anytime there's an actual anagram, you want to be ready to shuffle. Okay. I want to give you, I know we're like way over, but I want to give you the 2 other kind of weird versions that I feel like I see all the time. But how are you feeling? Like, okay, I think it's maybe starting to sink in. Like, yes, I need more practice, but like, are you starting to see how to build your anagram? I really like the anagram. Or your slots if you prefer. How are we feeling? 1, least comfortable. 5, most comfortable. No, you would have to multiply these 2 things out. And totally agree, Melissa. Like, I think it's easier to see with the anagram. So sketch them out. Sketch them out. Okay, an addendum. Okay, give this one a read. Yeah, I think generally the slot for me is, well, we're gonna see. It's a little tricky. I think the slot actually works better for more complicated things, but you have to be able to see what's happening with the like groupings. It's a little bit weird. If the answer choices are factorials, then it's a factorial one. But more often than not, the answer is the actual like number that you've multiplied out. Yeah. I just was like lazily not multiplying these things out. But we'll do it for this one. We're gonna multiply this one out. So thoughts on the anagram for this one? What's going up top? And if you're not sure, why does this seem confusing? Ooh, so Jenny said 3 juniors, 5 seniors. 8 slots for 8 total. Here's my question though. Can these 8 people be equally chosen? Like, are they the same 8 people? Or is there some distinction between them? So here's the critical piece for the anagram is that one anagram is only for a group that are equally choosable, which means I have to do 2 anagrams. I'm going to do an anagram for my juniors. This will be for my juniors. 1, 2, 3. And an anagram for my seniors. I can't. That didn't show up all, but there you go. And so this one will have what, 5? Okay, so here's my 1, 2, 3, 4 for my seniors. So let's make a junior choice. I'm going to choose 2 juniors. Sorry, I'm going to choose. So I'm going to put you on the committee. I'm going to put you on the committee. I'm going to throw you off. And then I'm going to choose 2 seniors. I'm going to put you on the committee. I'm going to put you on the committee, and I'm going to throw y'all off. Now, do I have to pick 2 juniors and 2 seniors, or am I picking 2 juniors or 2 seniors? Which means I'm going to do what? At the end, when I have numbers for my number of juniors and my number of senior choices. What am I going to do? If I have to choose 2 of each, boom, I'm going to multiply. Right, because it's an and. So this will be 3, and so we'll run through the math. This will be 3 factorial, 2 factorial, 1 factorial. And then I'm going to multiply that eventually by 5 factorial, 2 factorial, 3 factorial. So let's cancel this out. This one is 3 times 2 times 1 over 2 times 1. That one's 3. This is 5 times 4 times 3 times 2 times 1. divided by 2 times 1 times 3 times 2 times 1. So those will cancel. My 2 will cancel with my 4. So 5 times 2 is 10. I have 30 choices. So the exception to the anagram, we need to think about, okay, hold on. I don't have 8 kids I can choose from. I have 3 juniors that I'll pick 2 from. I have 5 seniors that I'll pick 2 from. So that's 2 different choices. I have to treat them as 2 different choices. Sure. Sure can. So the slot method on this one? No. I still have to do 2 choices. I have a junior choice and a senior choice. They're going to get multiplied at the end because it's an and. My juniors, I'm going to pick 2. My seniors, I'm going to pick 2. In both cases, they're going to be on committee. So I got to remind myself those are the same. Committee, committee. These are also the same. So how many do I have to choose from? I have 3 and then 2. For my seniors, I have 5 and then 4. And then in both of these cases, I need to divide by 2 factorial. So over here, I have 3 times 2 is 6 divided by 2. Over here, I have 5 times 4, which is 20 divided by 2. So I'm going to have 3 times 10 is 30. This isn't a 4 factorial right here. Remember, this was me expanding 5 factorial out. This is a 4. This is 5 times 4 times 3 times 2 times 1. That's literally a thing written all the way out. Yeah. We don't start canceling until we've written them out. Yeah, great to point that out. We do not start canceling until we point them. The one other weirdo. But how do we feel? Is this starting to like, okay, wait a minute. I'm starting to see. Starting to see it. This is the last weirdo one. I see this a bunch. It's done with like handshakes and tournaments. So the way we're going to set this up is either here's my 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's my 9 people. How many people play each other? 2. So in a match, it's 2 people where everybody else is out. So the longer formula would be 9 factorial divided by 2 factorial, 7 factorial. Now, a little bit of a shorthand. If I write this all the way out, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that is just 7 factorial. And so I can write this as 2 times 1. I can keep that 7 factorial the same, so I just don't have to write it all the way out. So then I'm going to cancel this 2 with the 8 that's left. 9 times 4 is 36. If I wanted to do this with slots, 2 people in a match, I have 9 people to choose from for the first team, 8 for the second, because they're both playing a match together. I need to divide that by 2 factorial. So this is going to be 9 times 8 divided by 2, which is exactly where we got on this one. Okay. Lots of questions on combinatorics, I know. Next time we kind of revisit this topic, we'll look at a few of the like kind of weird twists and then how this rolls into probability. Yeah. I had a great question about attending that Foundations of Math. So I did want to share with you that there's a fundamentals that I'll be teaching my, oh, I think I sent the wrong link. I'm so sorry. Let me give you the Foundations of Math link. So if you'd like to attend our Foundations of Math, I'm going to put the link in the chat window. For everyone who's attending online, you're welcome to come to manhattanprep.com /GMAT /classes /free. That's where you can come and sign up for like any of these free prep hours and things like that. But if you'd like to attend our Foundations of Math, those 2 5-hour free workshops, you can attend them. You also have the recordings once you sign up. The login for that is still, manhattanprep.com /GMAT. But this time it's courses, and I'll just kind of put it here. So if you want to pause the recording and grab this link, or maybe I'll have them put the link in the comment below. But if you'd like to do more practice on that, you can find it. I think it's also on this like CAP test version of it. Our GMAT courses, Foundations of GMAT Math. Yeah, there you go. I updated that thing. So hopefully this shows up for you now. Yeah. All right. Well, thanks so much, friends. I appreciate y'all so much. So many hard and ridiculous questions. So hopefully you feel like a little bit more able to approach some combinatorics. But again, my name is Whitney. Come hang out with us again. Have a lovely rest of your Monday or whatever time you're watching this recording. Come and hang out with us. Take care.